if you look at your strategies, we're going to figure out in the problem, what are the variables, what do we know, what don't we know. You may have two different types of equations. A primary equation is the equation that you're going to maximize or minimize. The secondary equation, in some problems you'll have one, and what it is, it's just an equation that involves the variables that you have in your primary equation. It will help you to eliminate some of those variables. So instead of having both x's and y's, you can get rid of one of the two variables. The domain for a lot of these problems, we're going to deal with things that you can actually measure, objects. So for a lot of the problems, your domain wouldn't include negative numbers. Maybe it doesn't include 0, things like that. And then finally, we'll use calculus, like the first derivative, to find maximums and minimums. And to find the first derivative, you would set that equal to 0 to get critical values, and then you could test them to see if they're maximums or minimums. You could also use the second derivative test to decide whether you have a maximum or a minimum. All right, so let's look at this first example here. So you have two positive numbers, x and y. Their product is 192. The sum of the first plus 3 times the second is a minimum. So let's do that first step where we come up with the different quantities that we have. So x is our first number. Y is our second number. And it says their product, so x times y is 192. And then finally it says the sum of the first plus 3 times the second, and that's going to give us a minimum. So those are the values that they gave us. This is that secondary equation. The only reason to have that equation is so I can eliminate one of the two variables in this primary equation here. So you can solve that equation for either variable, whichever one you prefer. I'm going to solve for y. Actually, when we go to plug it in, you'll probably see that x probably would have been the better variable to solve for, but it doesn't matter. So we solve for y. So in this equation then, I'm just going to call it m instead of minimum. I can take out the y and replace it with what y was equal to in terms of x from that secondary equation. Now I want to take the derivative of this. So I could take the derivative the way it is now, or if I want, I can simplify this thing here. And that 3 times that 192 is going to give you 576. And also if I bring that x up to the numerator, make it x to the negative 1, now I could just use my power rule for derivatives instead of having to use product rule there. So here's my derivative. Derivative of m would be m prime. Derivative of x is 1. Derivative of 576 x to the negative 1 would be negative 576 x to the negative 2. And to find critical values, you would set this derivative equal to 0. So I have 1. If I put this 576 on the other side, and then I can put that x squared in the denominator and make it over x squared. If you take this equation and cross multiply, you'll have 576 equals x squared. And then take the square root of both sides. Square root of 576 is 24. So you came up with one value. Now this one happened to be a nice round number. They're not all going to be nice round numbers. You may have roots. You may have irrational numbers, things like that. Okay, so let's plug this 24 then into this equation here, and we can get our y value. So 192 divided by 24, that's going to give us 8. So it asks, what are the two numbers? So my numbers are x is 24, y is 8. Just be careful that you answer the questions. Some of the problems are area problems. They'll ask for the dimensions, and you want to make sure that you answer the question that they gave you. So now the last piece is to prove that this x is 24. How do I know that this was actually a minimum and not a maximum? So you have two choices. So here's the first choice. So I can use my first derivative test. First derivative test is where you make your number line. Put that critical value of 24 on that number line. And then let's pick a value bigger and smaller than 24, like, I don't know, 20 and 30. I'm going to plug those values back into my first derivative. Here's my first derivative right here. Right? And if I plug in 20, you can plug it in using your calculator. You'll get a negative value. If you plug in 30 for x, remember this looks like this, 576 over x x squared. If you plug in 30, that's going to make this fraction into a decimal, something smaller than 1. So you'd have 1 minus something smaller than 1, which would be positive. And then you need to write a sentence, and that sentence would look like, since m prime changes from negative to positive at x equals 24, x equals 24 is a, think about what's happening here. If it's decreasing then increasing, that's going to make that a minimum. All right, the next example you don't have in your notes here, you can just, from this first page here, if you just slide this down a little bit here, just right underneath that problem that you just did, you can just add it in. It's not a super huge problem there, but we can put it right on that same page there. So you're going to have to add this guy in here. So this is, we'll make it 1b. All right, I'll paraphrase this one for you. So we're going to have 2 adjacent rectangular pens with fencing that is 1,200 feet. So 1,200 feet of fencing to enclose these 2 adjacent rectangular corrals. And we want to maximize the area. So, you know, let's come up with a diagram, what this thing is actually going to look like here. Change my pen. All right. So I have this 2 rectangular corrals here. This piece is the same length. I don't know what it is. I called it X. These pieces are all the same length. I'm going to call them Y. And I only need 1 piece of fencing in between the 2 of them there. So I have 2 things. I have perimeter. I have 3 X's. I have 4 Y's. And that's the fencing that they told me I have 1,200 feet of. Try to get rid of that. There we go. So I have 1,200 feet of fencing for that. I want to maximize area. So area is my primary equation. The area for this pen is xy. The area for that pen is xy. So I have 2 of those xy's. So this is the equation then that I'm going to go through and solve for either x or for y. And I choose to solve it for y. Like I say, you can pick whichever variable you want. So if I subtract 3x from both sides and then divide by 4, I'll have y is 300 minus 3/4 x. I'm going to take that then and plug it into this area equation. And again, remember, you don't want to have to do product rules. So if I distribute through the parentheses, I'll have 600x, and then I'll have 3/2 x squared. So there's my function. That's what I'm going to take the derivative of. So my derivative would be 600. And then 2 times that 3/2 is going to give me minus 3x. Set it equal to 0. So my x is 200. It's measured in feet. And then my y value, if I plug it back into that equation there, 300 minus 3/4 times x, which is 200. That would give me 150 feet for my y. So again, let's make sure that we answer the question that they ask here. So the dimensions, I'm going to say, because this is not real clear for this one, of each pen would be 200 feet by 150 feet. All right, so I've answered their question. And then the last thing is to prove that this was actually going to give me a maximum area. So I'm going to do for this one, I'm going to do the second derivative test. This is your other option. Instead of making the number line, you can do this. The reason why I do this is this second derivative is a very uncomplicated derivative. So my second derivative, derivative of 600 is 0, derivative of negative 3x is negative 3. So my a double prime, if this is less than 3, it doesn't matter what my critical value is. My second derivative is always negative 3, which is always less than 0. So my statement would look like this. Since a double prime, I could say it's always negative. It's negative when x is 200, but it's always going to be negative. That makes a, now we're talking about concavity with the second derivative. If the second derivative is negative, the original function is concave down. If you think concave down, it looks like that. So a is concave down, x is 200. So x is 200 is a maximum. Think about that concavity there. If that's 200, it has to be a maximum. So that's another option that you can go through and do. Either first derivative test or second derivative test. You don't have to do both, but that will give you that option there. All right, if you're not finished copying this, you can pause this and finish writing this down. All right, and then the last one we're going to do is this third one here, the print. And this will give you an example of each of the types of problems that you're going to see in the homework. So for this one, we have a piece of paper. It has 24 square inches of print. So inside here, 24 square inches of print. That's some length, that's some width. I don't know what it is. I do know that the margins at the top and the bottom are 1.5, and I know left and right they're 1. So the dimensions of the page would be this x for the print plus each of these little ones on the side here. So x plus 2 would be that width for that page. The length of the page would be the print for the y plus the 1.5 on either side there. So it would be a y plus 1.5 plus 1.5 would be y plus 3. So I have two equations. The area for the print is the xy, that gives me 24. And then the area of the whole page, which would be x plus 2 times y plus 3. So again, this is my secondary equation. We're going to get rid of one of those variables, so solve for either x or y. And then plug that into your equation that we're going to minimize for this one. So x plus 2, take out the y, make it 24 over x plus 3. And then for this, if you FOIL this, you can use power rule again. So x times 24 over x is just 24. Outer times outer would give me plus 3x. Inner times inner would give me 48 over x, or 48x to the negative 1. Last times last is 6. And then I can combine some like terms together here. This 24 and this 6 will give me 30. I have 3x, and I have 48x to the negative 1. All right, and ready for the derivative. Derivative 30 is 0, derivative 3x is 3. Derivative 48x to the negative 1 is minus 48x to the negative 2. Set it equal to 0. I'm going to put that x squared in the bottom, make it a positive. And cross multiply. Divide by 3, we get 16, so my x is, I'm only going to write down positive 4 because we're talking about the length of a side. It can't be a negative value there. So my x value is 4. If I plug that back into this equation over here, I'm going to have 24 divided by 4, which is 6. They want to know what are the dimensions for the page. Well, the dimensions of the page were x plus 2 by y plus 3. So we'll plug those values in. So x was 4. 4 plus 2 would give me 6. And y plus 6, or y plus 3. 6 plus 3 would give me 9. So that's the dimensions of the page. And then finally, we can decide whether we're going to do a first derivative test or second derivative test. I think we'll do second derivative test for this one. I'm just going to squeeze it right in here to prove that we actually found it. So my second derivative, here's my first derivative. Second derivative, 3 would be 0. I'd have negative 48 times negative 2 would give me positive 96. X to the negative 3. If I plug in, x was 4. I'll have 96 over 4 cubed. I don't care what the number is, but it's positive. Since a double prime is positive, that means a, the original function, is concave up at x equals 4. So x equals 4 is a concave up minimum. Right. And if you're not sure, draw something that's concave up, and then you'll be able to see that that's a low point in the graph there. Okay, that is it.